coming. This is about Azure Files, which is a fully managed share, SMB share in the cloud that can be accessed from anywhere in the world, as well as within an Azure VM. And specifically this talk, towards the middle of it, is going to go into how we manage to make major changes to the underlying schema in a completely transparent way so that users aren't aware of it, which is usually something that's very difficult to do. Quickly, just to go over the topics, first is a review of the design, and then describing this change that we made, which is for large file shares. And after this, I'll just refer to LFS because it fits better in PowerPoint that way. And then how, in general, we do add new features with very minimal downtime, zero downtime, really, because we can't afford to. It has to always be available. This is very quickly a protocol history of SMB. I'm going to skip this, but if you want, the slides will be out and you can read all about it. We do SMB 3.0 right now in Azure Files. We're working on 1.1. Really, the features you get in 1.1 aren't that much more. The 3.0 was a really big one. Fundamentally, Azure Files is not just running serv2.sys on an Azure node. It's fundamentally different. It's a completely rewritten SMB server using Azure Tables and blobs as a backstore. If you've ever read the MS SMB2 protocol doc, it always talks about the store, the object store below you. And so we didn't have a file system we're writing to. We're writing just to this blobs, the page blobs on Azure, and then the Azure Tables for the metadata in order to store the data in a very resilient way. Because those are already primitives that existed on Azure Tables and blobs, and so we're able to leverage all the work that went into those. Currently, this is some of the limits that we have and some of the status of things. So the ones that I have in parentheses here those are the ones for the LFS that are currently in preview, and they're much larger numbers. And so that's going to go into like how we made changes to actually accomplish that. But I'm going to go kind of through this quickly here. We also have Linux support. This is the current client support for talking to Azure Files. Specifically, it's SMB 3.0, and encryption and persistent handles are the two most important features that we need. With encryption, one of the really cool scenarios you have is you can actually be anywhere on the internet and access an Azure file share. Because it's encrypted, we have end-to-end encryption. It's completely secure. And the integrity, so it can't be tampered with or observed. And the way it's accessed is via a URL like this, which is your account name and then filecore windows.net share name. These requests come into a software load balancer, which is the actual endpoint where that lives. They can either come from the internet over here or from an IaaS VM, which means it's inside of an Azure data center. This obviously has much lower latency than this. But this does work, which is pretty cool that it works at all. It's very handy sometimes when you're in the middle of nowhere and just all you need is an internet connection with port 445 outbound not blocked, which is sometimes a problem. But then you can go and access any files. They come in here, requests then get the software load balancer hashes the TCP/IP header and will assign this connection randomly, effectively, to one of these front ends. And then that will own the SMB connection. For requests coming from the client on that connection. Generally, you have a one-to-one relationship between sessions and connections, but not always. We have some customers who create many sessions per connection. It really depends on the client, what the client wants to do. It's all legal in the spec. And then the front end is the one that actually does the parsing of the packets, and then it goes and speaks primitives down to the Azure Table and Blob Store to do the managing of the metadata for the namespace and the page blob for the actual file data. Yes?
What kind of encryption and who has the key?
It's a CMAC, AES CMAC 128. The key is it's a session key. It's a shared secret between the two, and it's established during the GSS negotiation as part of it's NTLM v2. So that's how you actually authenticate, and we have very long keys. So it's actually, as long as it's relatively strong, though, because of Kerberos, you don't have two-way authentication. So this allows the server to authenticate the client reliably, but with NTLM, one of the issues is that you don't have the two-way, so it's difficult for the client to authenticate the server.
So the on-disk data is not encrypted? It's only for the channel?
The channel's encrypted. Separately, we do encrypt everything on disk, but in a way that's not even advertised. We just do that out of paranoia, really, because we worry about people walking out of data centers with disks. So separately, everything down a low level, when we actually write to files to store these actual blob, the really low level, that's all encrypted on disk. But that's kind of orthogonal to the encryption that we do over the wire here.
Yeah, actually the question was a bit about the security from the client perspective. Do you have the ability to inspect the data of the client when you store it on the Azure table?
Because we're part of the whole negotiation, we could get the session key eventually and then go in and retroactively decrypt it, as the client could as well, because it's a shared secret. And then once it goes on the table blob, the keys are stored separately from the actual data. I mean, so of course you have to be able to retrieve that because the customer wants to be able to read their data, not just write it. So yeah, there is, but it's separated such that if somebody went and stole a bunch of disks, they wouldn't have anything. So that was the scenario that we were concerned about. This talk actually is on the Z drive, which is actually an Azure file share. So you can see here that this is actually an Azure file share. It's the syntax I talked about, David Go West, file.core.windows.net. And so I actually ran my PowerPoint file from this share. And furthermore, because I just didn't get around to setting up anything in Europe, this is actually a share that's hosted in the Bay Area in California. So it's halfway around the world. And it's not the quickest connection, but because it has all the correct semantics for a file share, it just works. And you can basically do sorts of I/O here. Well, this is really small for me to read, but for instance, you can go and bring up here. And so this is the file share. And one of the things that we had, one of the interesting things we had to do is, of course, we had to support change notify, because a lot of programs depend on that. So it's deleting those, and then the change notify picks it up. And so if I go back to another feature that we have here, that because it supports all of the SMB primitives, and as I mentioned, it was 5 terabytes currently, and we're doing the large file share. That's Microsoft Azure File System is the name of the file system. And then we also have the previous versions, which is supporting the vol snap, the snapshot syntax. So this is actually a previous snapshot I took of this volume. And so you can basically operate it just like you could in a normal file share. The reason you asked why would you do this is because we can basically take programs that were written for a file API that maybe the person who wrote it retired 10 years ago. It's a vertical application in a company. They don't want to rewrite it, or they can't. They don't have the source code anymore. And things like that, if they want to move from on-premise file servers to the cloud, it kind of just works. They can just move it there and just change where they're pointing their network share. So it's very useful in those conditions that we call it. The term is lift and shift. You take their existing workload and just move it into the cloud. REST is kind of a big buzzword in the cloud, and most everything in cloud-oriented uses REST. And so what we did is we allowed the REST APIs that normally work on blobs to access also the file namespace in a coherent way. So for instance, if you do a read, then you can do the get blob. And if you have byte range locks, it will respect those. If you have leases, for instance, doing a write, it'll break the leases correctly. So effectively what we do is, for these operations like put, it's effectively an open write close. And so it emulates that as a single transaction. So it does all the side effects that would happen if you did those via SMB. So the two can operate at the same time together. And because of that, if you wanted to, say, rewrite your applications using REST, you could do that gradually, because your data doesn't have to move. It's all in the Azure file share. This is, again, taking a look at how data, a little bit more detail. It comes in here to our load balancer. The front end node picks one of them, and then these are just requests to do a low-level object access to either the metadata for the tables or the blob store for the data. Yes?
For large files, on what boundaries do you segregate the blobs? I mean, suppose I have a VM image of 40 GB.
Yeah.
Would you segregate it into separate, smaller blobs?
Well, it's the extents. At a very low level, there's stored these extent files, which are a few hundred megs, but those can store files from multiple streams together. We're so far removed from when the actual files are actually stored to disk. And in fact, when you're doing writes, in order to make writes more efficient, so we can act them faster, when you do a write on Azure for anything, we don't return success until we've replicated it 3 different places in the data center. And so in order to make that reasonable on spinning media, all the nodes have flash storage that we journal to. So as soon as we've replicated it on flash on 3 different nodes, we can ACK it, and then we destage that journal to spinning disk offline. SMB is stateful, so this makes it particularly difficult to do active-active clustering, because if a front end dies, all the information about the handle has to be seamlessly be able to reconstruct it on a different front end, and therefore that has to be persisted in the back end, whereas normally that would only be stored in a server's memory. So normal server implementation, if the server crashes, you lose all your handle state. But with Azure Files, with persistent handles, you don't. You're able to basically seamlessly reconnect. And this goes into the Azure, how we use Azure tables and blobs. Again, the blob is the data, and the table is just an Azure Tables and NoSQL table with a collection of rows and keys. The coarse granularity are the partition keys, which are how we describe, that's how we delineate partitions in an Azure table, and the key distinguishing factor of our partition is that's the level at which we can do atomic transactions. So we can have multiple tables, and as long as they have the same partition key, which, as a little getting ahead, is for our currently deployed one, is the account name and the share name, then we can do atomic transactions over that very easily. And so that was very convenient because shares are the natural unit of breaking up. These are some of the tables that we have, and again, we can make changes to multiple of these tables atomically. It's very easy. We just simply say we start a transaction, and we can make changes to all these different tables, and we either commit or abort. So from our perspective as Azure Files, it was very easy, but it's because all the hard work is being done by this table interface, which was already written and used for Azure Tables. And you can see here this pretty self-explanatory. The file blob handle is very important. That's for all the handles. And that comes into play when a front end dies and we have to reconnect everything. We need to remember everything about that handle. This just reiterating that by leveraging the Azure Tables interface, we're able to go and do these atomic transactions over just the range of the partition. And again, the partition right now is currently a share. And that shows us here. This is the partition key and the row key. So this is what defines the unit of atomicity in transactions on a row. And all those rows, all those tables that are listed in the previous slide, all have these first 2 columns. And so that means that they're able to go and all participate in the same atomic transactions over a share. And a share is a very natural place to split it up. And then row keys are just how you can sort and find by file ID. Then share version is for the snapshots. And namespace is effectively where the directories are. It's pretty straightforward. It's like anything else. It's just the namespace and then the file ID space. And then what we're doing now, this change that we've had, is increasing the partition key to include the file ID. Because what this does is it allows us to go and split up partitions into smaller pieces, so then we can expand much more. And so it's able to scale much better. Because now instead of having everything being owned by a single backend node for one partition encompassing an entire share, now it's just a small part of a share. And furthermore, we have components that actively look at how partitions are being used, and all the time we're splitting and merging them and transferring ownership in order to maintain equal load. Back when we were very strict about only a share, the normal components that manage that load weren't able to split us up because we had to be on one partition. And so this also helps our load managing software do what it's supposed to do. This is how it currently is today. We have the front-end nodes that talk to this one back-end node who currently, that's the node that owns that partition of the table, which currently is one share. And then these EN nodes are where the actual file data is stored. And what we've done is now have multiple back-end nodes for a single share because we've partitioned that file ID space. And when we allocate file IDs, we actually mirror them so you get a lot of good dispersion, because otherwise you wouldn't do well. If you're sequentially creating files, you want to spread those out so that you can scale really well for just copying lots of files to a volume, because they'll tend to get sequential file IDs otherwise. And this is another way to represent it. Currently, this is how it works. This back-end node is the one who owns the partition, who owns that partition, which in our current version that we're shipping is a share. And metadata, all these metadata like opens and closes, all go to this back-end node here, which is the one that owns the share and therefore has all the control over the metadata, and it's able to do those atomic transactions over all those different rows. And then write data, writes all flow through this one as well. Reads, however, are able to go from whichever, all these different front ends are basically different connections coming from all over the internet and all over VMs that they establish a connection to Azure Files and they just happen to land on one FE or another. And then once they're there, the actual files that they're opening, that file data can live on any of these EN nodes. And they are able to read directly from those nodes. So they're able to bypass that. So reads completely fan out. And with the new large file share, what we've done is that a single share now is split up into multiple back-end nodes because we partition on the file ID instead of just the share name. And so for namespace metadata, in order to make this at the first stage much more doable, that is still owned by a single back-end node. And that makes it so that we can, things like rename are much easier then because we have all the actual, we can still do atomic transactions over that. And then for file metadata and writes, file metadata would be like file size. Because one of the issues is that you have to, extending writes, for instance, have to change file size. And that's something that used to all go through one backend before large file share. But now with large file share, we need to replicate that file size to all these different backend nodes so they can correctly go and fail reads or extend writes. And that's become more complicated and required distributed transactions. So that now the file metadata and the file write data is able to go and spread out among more than just one backend at least. So this is because this is all partitioned by file ID now. And then again, the reads are all many-to-many. So you can see here there's still room for optimization in terms of this file metadata, the namespace metadata if it proves to be a significantly limiting factor. So we have this change in schema, which is actually a pretty big change. And so we would need to do this in a way that was completely transparent. And so the way you do this is you go through many stages in a process where you have, first you introduce code that can understand both versions. And then once that's fully deployed, then you introduce code that can write both versions. And then once that's fully deployed, then you stop writing the old version. And once that's fully deployed, then you go and only read the new version. So it's this process that takes a long time to go through. But by doing this, it makes it so that it's completely transparent to the customer. And for handles that are open but not being used, those happen kind of lazily. If a handle is used, we take that opportunity to do it right then, to do that file row migration, to change the schema, because that's an opportune time to do it. One of the things that is useful about having this different states of front end, back end, is that we're able to tier data by durability requirements. For instance, when you connect to an Azure share, the TCP port number, we don't need to persist that because it doesn't matter. If the connection dies and we reconnect, it's a brand new data. But for instance, the handle ID or the session ID, that has to be durably persisted, because when the client reconnects and attempts to reconnect all those handles using persistent handles, they've got to have all that data still valid. And so normally this would only be stored in a server's RAM, but for Azure Files, it's durably persisted 3 times. So when you open a file, instead of just incrementing an open count on a normal server, we have to actually persist all that durably in 3 different copies across the data center. So a lot's happening when you open and close a file. It still is about 9 milliseconds. Persistent handles are new in SMB3, and this was actually really important for us because we restart our front-end nodes so much because we're updating its software, and so we just randomly go and restart, kill our processes on nodes, which causes the client to reconnect. And persistent handles that was introduced in SMB3 allowed us to do this in a way that would be transparent for the client. It's called transparent failover. It goes and sends a reconnect request, and it has state that it remembers on its own. So it's able to basically give us clues about has a crate GUID that it sent us on the original query. Because there are some requests that are once only. For instance, if you specify disposition of a file create, which means that create it and fail if it's already there are cases where we could have already executed that create, but the client didn't know that because we died before we got the message back. So when we get that same message again, we have to recognize this is a replay and just to no-op it and say, yes, it worked because we actually did it the first time. This shows how the actual works in terms of what's going on. You have client A and client B just reading and writing. They could be reading and writing the same file, just connected to different front ends at the same file at the same time. And then client B loses their connection. So they connect to another front end who then reestablishes all the handles that were open. And actual applications running on client B are completely unaware anything happened. There's maybe a slight hiccup, but we restart these front end nodes all the time. So in a way, we really are testing all these boundary conditions at least once every couple of weeks because we were rolling out new software. These are some of the observations that we learned actually after this had been running for a few years. Is a lot of people tried to take applications that they had run only on a locally attached storage on a disk, and then tried to run that immediately on Azure Files, and didn't even try on a local file, on a local share first. And what you find is that things like opening and closing a file, especially opening a non-existent file, can get very fast on an NTFS volume because the MFT is all cached, the directory is all cached, and so it's just a handful of microseconds that says no, it doesn't exist. But now they come all the way over the wire to us, and it takes us a while. So it's orders of magnitude longer. So if you have a program that spins trying to open the same files that don't exist all the time, that may have been bad on a local system, but not bad enough that you would notice. But now you run on Azure Files, and it's really bad. So we implemented direct releases, which will help that hopefully substantially. But in general, there are some programs that could have been written away that just make it very difficult to go and port them, or basically lift and shift them so they get very similar behavior that they got on a local machine, especially if they never even ran it on a local share. They only ran it on directly attached storage. And this is an interesting graph where it shows the distribution of requests, and the left is by, yeah, it's up there on the part you can't read here. Percent of request type. So this is a breakdown of different requests, the SMB requests that we get, and the right side is by total end-to-end time, and the left side is by total number of requests. So those are both interesting metrics. One is just the number of requests we get, but then also what's interesting is how long we spent on each one. So that's like the total latency the client experiences. And what you see here is that it's create, close, read, and write. Are pretty much all that matters. So you have these 4, 1, 2, 3, and that's the 4th one there. The colors are a little hard to read, and then basically the same thing here in different states. For instance, so the reads take longer, but they're actually smaller in number. But everything else here is kind of not that significant. So that one, and then that one. So optimizing open, close, read, and write is very important because that's how we basically go and try to get overall the performance better, which is one of the motivations for splitting up this partition so we could scale much better, especially on reads and opens and closes, because now it's not just one back-end node that has to own the entire share, that responsibility is split up. But it did make it difficult that we had to add some distributed transactions to make that work.
Why do you need close to take a lot of time?
Close is one of in Windows, a lot of stuff happens at close time. If you go and write to a file, and you don't update the timestamp right away. You don't update the file size right away. That all happens at close time. So it's just the Windows semantics. When you open a file and do reads, writes, and whatever, we wait until close to update all those things. And all those things are all these different tables that we have to update. And change notified, that's another thing too. So when you actually, if you wrote to a file, it's when you close the handle that we notified the change notify. And we've got to go and find everyone that is registered change notifies. We've got to break file locks. We have to break leases. There's all this book housekeeping that happens at close time. It's actually the most expensive. Yes, because I mean, our guarantee, our contract with the caller is that we will not act your request until it is durably, everything that we're supposed to do here, we have guaranteed to you that is durably committed. It's very different than when you're talking to a normal server and you're not doing write through. It's very lax in this. If you were doing a robocopy or an Xcopy to a Windows share that's not all write through and you pull the plug on the Windows server, what made it or didn't make it to the server is kind of random. Right? But with Azure Files, is every single request that was ACT is there. It's done. It's durably persistent. These are some specific things that were pain points. Windows semantics are that when you actually delete a file, you don't really delete a file. You actually set a disposition saying, I'd like it to be deleted when the last file is closed. And if you leak handles, if your application leaks handles and files don't go away, and this is especially problematic for people running on Linux clients, because in Linux, the unlink request, it removes it from the namespace immediately. And so it causes app-compat problems. Because in Linux, they leak a handle, it's not a big deal, but in Windows, it causes it. Now, this would have happened talking to a Windows server as well, but we have a lot of, I don't know the percentages, it's a significant percentage of our customers are actually Linux clients. And that's causing a problem. And because when you're running on a Windows server, you can actually sit in front of the server and do a net files ID/close. And physically force close a handle, but we don't actually have, a customer doesn't have that ability. We have it, our internal support people can do that, but that doesn't really scale well. So that's been a source of problem. Let's see, how am I doing time here? Okay, 3 minutes. So that's why lack of server management. There are these tools that people have gotten used to talking to a normal Windows server that they could do if they actually were sitting in front of the server, but they aren't. This is a kind of a really nasty one. This is append only. When you open a file for write-only access, we can't cache it at all. And the reason is because if you don't have read access, then the cache manager on the client can't read whole pages of data to fill the cache because that handle doesn't have read access. So its only option is to send out exactly what the Win32 API call was to do a write. And there are people apps who open, like do fopen file, foo a, and then do write 1 byte, write the next byte, write the next byte. 20 megabytes later, they're done. And this is like the worst imaginable thing for Azure Files because every one of those is an extending write, and every one of them we have to wait to replicate it 3 times before they can move on to write the next byte. Whereas if they just specified read write here instead of append, all that would have happened locally. They wouldn't have blocked their app at all. It would have been all copied into the NT cache, and then when they close their handle, it would have all been written orders of magnitude faster. And we've actually talked to people about this, and some of them are philosophically opposed to requesting read and write because they don't tend to read it. And I understand that, but it really makes a huge performance impact. Because it's a shared commodity in terms of you have what's called noisy neighbors, which is if you happen to be on a tenant or a particular cluster node that someone else is on that's doing a lot of noisy stuff, that you could be impacted by them. So the actual predictability of your performance is much more variable than talking to a local disk, or even to a server that you own, because you own all the load on that server. Because we have a shared namespace with REST is sent via HTTP. And that has certain limits on total size and number of path elements and character sets that you don't have on SMB. SMB is what's called UCS2, which is basically just a bunch of U-shorts. Aside from the special characters that aren't permitted, which are all in the lower part, less than 128x. After that, it's just a bunch of U-shorts. And so there are names that you can create on SMB that you then can't create via REST. So we basically had to go and limit it to the lowest common denominator. And other than that, just basically poorly written apps that just, they work okay on a local disk, but then when you try to run them against Azure Files, all of these inefficiencies just become very much more apparent. These are some resources that are available on Azure Files. This is our large file share announcement. This is the one that is kind of the topic of how making this major schema change and how we can do that without having any downtime or the customers even being aware of it. And that's it.